Okay, now we'll be moving to our next topic, which is basically from unsupervised learning, and more precisely, we'll be looking at autoencoders, right? So, just a little preamble before we dive into the technical details. You see, so far in the first 7 weeks, we have been targeting supervised learning, right? We have all the examples we have seen first in, you can say, MLP, and then CNN, and then different architectures of CNN. So our prime focus was on classification, right? That you have some data. Data can be anything, image or numbers or anything that you can think of, and you have a class label. Okay, so you train a model, and then once the model is trained, you actually give it or feed it with unseen data, and the model is expected to predict the class label of the unseen data, right? So this is a typical supervised learning framework where you have data which is conventionally represented by the symbol X, and you have labels which are commonly represented by the symbol Y, right? So you have X and Y data as well as label. Now we are slightly changing our theme of discussion from supervised to unsupervised learning, where you do have data, but we don't have any labels. Okay, labels can be present, you can say, but we don't need them, right? So, and within unsupervised learning, we'll be discussing autoencoders in detail, right? So I hope we'll conclude this topic within, say, 30-40 minutes, right? So let's see the technical details, what an autoencoder is and what are the applications where it can be used. Okay. Okay, so in simplest words, an autoencoder is actually a neural network, a feed for neural network, right? And what is the objective? You feed it with some data, say X, and the objective is to predict X, right? So for example, if this is my autoencoder, just forget about the inner part. So I feed it this image as an input. Okay, so this is my input. But the slightly strange thing is that what I expect as an output is the same thing. Okay, so whatever I am feeding as an input, I want the model to generate the same thing as the output, right? So for example, if it's an image represented by, say, 28 by 28 image, so it means there are 784 values. If it's a colored image, there are 3 times values. So I have these many neurons and the input and the output layer, right? So if you look at this idea for the very first time, it seems a bit strange, right? That why are we doing this? Means what are we gaining? That I feed some data as an input, and I'm trying to learn the weight matrices which will produce the same thing at the output, right? Initially, it seems like that this is totally useless. What will we do with such a system, right? So maybe other than pictures, you are familiar with these digits. I feed it digit from 0 to 9, and if I feed it 0, I expect it to reproduce, right? So actually, the usefulness is that when we are feeding this data to this network, right, which is a simple MLP, right, nothing fully connected layers. Okay. So you see, maybe we have 784 neurons here, right? Maybe I have, say, 120 here, and suppose 32 here, 120, and again 784. Okay, let's forget about the color. So let's talk about grayscale image. So the thing is that this part of the network, it is taking the raw image and representing it in a compressed form, that is 32 numbers, right? So this part of the network can be considered as an encoder, that you are feeding it with an image. It is taking the dot product of input with the weights which it has learned, and then it is representing your data in a compressed form of 32 values, right? I'm assuming that I have 32 neurons in this layer. It can be any number. I'm just assuming it for the sake of discussion, right? And then this part of the network takes this compressed representation as an input. It again takes the dot product of with all the weights that it has learned, and eventually it reproduces the output, right? So this part of the network can be considered as a decoder, which is taking the latent or bottleneck or compressed representation, whatever you want to call it, and it is decoding or reproducing the image, right? So actually, we are more interested in this central part, which is the compressed form, right? So one straightforward you can say application that you can think of is that you can represent data in some compressed form, right? Although this is not very ideal, there are many sophisticated ways we can do that. But with the discussion that we have done so far, one obvious application comes out to be that, okay, if I have something trained like this, I can represent my data in a compressed form, and later I can use the decoder part to reproduce the data. Okay, so far this is what we can think of. We'll develop this idea further. Okay, so this is a visual illustration of, you can say, the same concept where suppose the model is already trained. How it is trained, we'll see in a while. So we feed it with some image. This is the encoder part, and this is your compressed representation, right? Maybe 784 was represented into 32 numbers, right? And then you, if the model is trained, you feed it to the decoder part, which will reproduce the input, but of course it is lossy, right? Lossy means that it is not a perfect reproduction of what you feed as an input, but it is very close to it, right? For example, if the first pixel here was say 0.1, so maybe it is 0.11, and similarly if this one is like 0.95, so maybe here you have a pixel which is 0.94 or something like that, right? So it is not 100% exactly the same set of values you have, but more or less similar values. It depends how good your model has been trained. Now you see, once we are training such a model, we have data. Okay, so previously in all the classification problems and in your assignments as well, you have been very frequently using this to train a model. X, Y, right? X is your data, Y is the label, right? So this we have been using many times. For example, if this was our data, so these are the labels, we have softmax, and this is how we train it. But now you see there is no Y. Why? Because we are in unsupervised domain, right? We only have data, we don't have label. Even if we have label, we don't care about them, right? Because we are not implementing supervised learning. So now you can guess that instead of this, what we'll be using when we are training a model, this is our input, model.fit x. But what is output? What are we expecting at the last layer? We are expecting the same thing, right? So this is a key, you can say, concept that when you call the model.fit function, which actually implements backpropagation, so unlike supervised learning where you used model.fit x comma y, you have model.fit x comma x, right? So this x is actually your input, which is what you are feeding, and you want the same thing as the output, right? So that's why if you look at this for the first time, it may sound a bit strange, but in case of autoencoders, will be when we implement, we'll be using this model.fit. Whatever is the input, we want that as an output. Okay, now you see, in we want our autoencoders to be non-trivial. Now, what does that mean? Okay, let me just quickly make a you can say a model maybe on the board so that we have some space. Okay, and let me say that what actually we desire. Suppose I have an image, again the digits, right? So I have 784 neurons here, right? And I feed it with some digits in 9. And suppose I don't have anything in between. This is my input layer and this is my output layer. Okay, so what I do is when I make these connections, okay, so I say, okay, this first neuron is connected to first neuron, so this weight is 1, rest all the weights are 0. Similarly, when I use the second neuron, okay, so what I do is I say, okay, I have all of these connections, something like this. So when second is connected to second, so the weight of this is 1 and all the other weights are 0. Okay. So if you do this, your weight matrix is actually an identity matrix, right? Something like this. Okay, you can extend it. I have just written a few values. So it means when you will feed 9, you will get 9 at the output, right? But this is trivial. Trivial means we are not gaining anything with this. Well, it is like a buffer. What you are feeding, you are multiplying with 1 and you are getting the same thing. So this is what should happen. Means I don't get anything useful from this implementation, right? So that's why we say, in order to make it non-trivial, what we do is that when we are implementing an autoencoder, we add a bottleneck layer, where the dimension is much smaller than the input, right? Only then this will be useful. So in order to explain this, you see, so as I told you, suppose your input is 784, then we have 100 neurons, and then this is our bottleneck layer, 20 units, right? This is the compressed representation of this. And then you actually expand back your dimension 100, 784, and so on, right? So this is basically, if you have an implementation like this, only then autoencoder is useful, because then you can use this you can say coded representation or compressed representation for something useful. If you just connect input to output, all the weights are one, it is trivial, it is totally useless, right? So this was the idea of when we say we need to have a bottleneck layer where the dimensionality is much smaller as compared to the input. Okay, now let's see, as we discussed in the earlier slides, how we can use an autoencoder for compression purposes, right? Although practically it is never used, but theoretically we can discuss, because this is the most obvious application that comes to our mind when we see autoencoders, right? So if you're doing, or if you're using autoencoder for compression, you must keep in mind that the compression and decompression that you will do using an autoencoder would be data specific, lossy, and unsupervised. Now I'll explain each of these, that what does it mean by data specific, lossy, and unsupervised, right? So suppose you have an autoencoder, right? Maybe something like this. This is your autoencoder, right? I draw it like a box, and you train it on MNIST digits. Okay, so it is now trained, right? If you want to compress some data, right? For example, the digits in the CVL dataset, you will pass those through this trained model. You will make a forward pass, and whatever coded representation you have, you can save it to the disk or whatever you want, transfer it over a network, whatever you want to do it, right? So actually you are compressing it. Similarly, when you want to decompress, you can give that data to the decoder part, which will actually generate you back the images. Now the thing is that if this autoencoder is trained on MNIST and you are using it on CVL, then it is acceptable, because both of these data sets are representing the same thing. They are handwritten digits which look quite similar. On the other hand, if you have trained this on MNIST and suppose you start using it to compress images in the ImageNet dataset or Microsoft Cocoa dataset or any other dataset, Pascal dataset, then this will not work, right? Why it will not work? Because it has been trained to reproduce handwritten digits. It can only compress and decompress the data or similar data to which it is trained. You cannot expect an autoencoder trained on MNIST to compress and decompress images, maybe colored images, landscape images, or something different, right? So this is one point, which makes sense, right? Because when the weights were tuned, you actually gave a handwritten digit as input and the same handwritten digit as the target. If you feed some other images, of course it will not give you any error. It will produce something as an output, but that would be meaningless, right? It will not actually be performing compression and decompression. The second point is lossy, which we already discussed, that whatever you reproduce is not exactly what you actually encoded, right? And you must be knowing from your previous knowledge that when we talk of compression, right, you must have heard of like JPEG, maybe TIFF, right? So JPEG is, for example, lossy, right? You gain a lot of compression, right? Maybe a file of 1 MB is compressed to say 100 KB. So compression is more, but you lose some information, right? On the other hand, maybe TIFF is in which you do not gain much compression, but it is lossless. Lossless means whatever you encode, you get back exactly the same thing, right? So autoencoder, if you are using them for compression, this is a lossy compression. Lossy compression means if I have an image 2, 3, 4, it may be something like this. So when I decompress it, maybe I get like 1, 4, 5, right, which are very close values. Visually, they look similar, but actually it is lossy, right? Because you are not getting back the exactly same value. When it was 3, you are getting 4 or 2 or something similar. And the third point, unsupervised, we have already discussed that in order to, you can say, train an autoencoder, we just give it raw input data. We don't need any explicit class labels to work with autoencoders, right? Now, how this will work, right? So we have already seen encoding function, which is just layers of a neural network. Decoding part is also a layer of a neural network, right? But you need some way of comparing the input and the output, which is like your loss function. Okay, so as I told you, what can be the loss function? For example, if the original, this is an original image where the first value was 0.1, and here you are getting say 0.2. So what is your error? 0.2 minus 0.1. Similarly, for the second pixel, if the value was say 0.5, and here in second pixel you are getting say zero point 0.6, so what is your difference? 0.5 minus 0.6, and so on, right? So you can actually square them and add them, which is mean square loss, or you can take the absolute values or add them, right? So basically you need some distance function which can actually tell you or quantify that how much information you are losing. Okay, there are different methods: signal to noise ratio or mean square error, absolute difference. You can use any of those, right? So this is basically you can say an important component where you must know that how do you compute the difference between the input and the output, so that you can reduce that error and you can train your model, right? Okay, so as I told you that um, theoretically you can use it for compression, but practically no one will use autoencoder for compressing data or maybe images, right? Why? Because you have standard data independent mature algorithms available for compression, right? If it's a JPEG compression, there's a standard algorithm. It will work on every image. Of course, the amount of compression you achieve will depend upon many parameters, but you don't need a separate JPEG algorithm for different types of images, right? You have a standard JPEG algo for images or MPEG for videos. You just implement it, you pass it data, it will be compressed and decompressed. On the other hand, with autoencoders, you need a separate autoencoder trained on a particular type of data, and it can only compress and decompress the data on which it is trained, right? So that's why it is not practical that you use it for compression, right? So, but theoretically it can be used, but there are other practical applications where autoencoders are useful, right? One of these, which we'll see in detail, is denoising. Denoising means removing noise from an image, right? I'll give you more details on how this will work. And of course, it can also be used for reducing the dimensionality, right? For if you have high dimensional data, you can always, you want to bring it to some lower dimension like PCA for visualization purposes, okay? So you can actually use an autoencoder as well, right? So just to give you an idea that we are trying to resize an image, maybe with PCA and with autoencoder. So it is known that autoencoder is likely to produce visually much better results as compared to PCA, right? But anyways, we are not looking at this dimensional reduction. Our major case study is basically denoising using an autoencoder, right? So now let's first, you can say, implement or design our very first simplest possible autoencoder, which we normally call vanilla network or vanilla autoencoder, where we'll be using only fully connected layers, right? What are fully connected layers? Simple MLP, no convolution, no nothing, right? So what we'll do is we'll choose some architecture, right? That how many neurons I need in different layers, how many layers would be there. Of course, for input and output, you don't have choice, right? If whatever is the size of the image, that is your input and the same is your output. Yes, you can choose how many layers you need here, what are the number of neurons in each layer, okay? These you can choose, you can train it with model.fit x comma x, and then you can actually feed it with data to have a coded representation, or you can say a bottleneck representation of that data, right? So this illustration shows you the data that is fed to a trained autoencoder, right? The first row actually, this represents the input images, okay? The middle row is actually a visualization of the, you can say, compressed representation, right? It is 4 cross 8, right? So it means these are 32 values. Okay, so we have compressed 784 values into 32 values. Now you see, visually, it does not look anything meaningful, right? It is, you cannot tell what it is. But when you pass these 32 values through the decoder, which is also trained, so you get back the original image, right? By original, I means very close to original image. Of course, it is lossy, to it, so it is not 100% copy of that, but still, whatever you are feeding, if you compare the first row and the last row, so they are pretty much similar, right? Maybe we are losing something here, right? Maybe this is a bit blurred, but still more or less, if you do more training, maybe the results are visually even better. Okay, so this is, you can say, a visual illustration of what we'll be trying to implement, right? And I'll be giving you a walkthrough of the source code in TensorFlow, right? With some key details, so that once you have to implement it for some task, you can do it easily, right? Okay, so on the next slide, we have this implementation. So I'll slowly go through it, because previously all the models that you have implemented, we have been using sequential API. Sequential API is relatively simple to implement, right? Because you create a model, right? You write model, and then you simply write model dot add, and you keep on adding layers to it. Okay, so for if you add 2 layers, it would be something like this. So you just keep on adding layers. So from the viewpoint of implementation and understanding, sequential API is very good, right? But it is not very flexible, right? Why am I saying this? You have seen RESTnet, right? In which you have maybe this layer connected to this layer. Now just think how we can manage this in sequential API. Because in sequential API, we are just stacking layers one after the other. So it means we need a relatively flexible way, so that we can connect anything with anything, right? Of course, in autoencoder, this is not required. You can easily implement an autoencoder with sequential API, but just to give you some flavor of functional API, the example which we have here is with functional API, right? So let me just, because this is the first time we are looking at it, so maybe I can give you some more details that how it works, right? Because from the viewpoint of syntax, it is not very straightforward, but with some practice, you can actually develop a good grip on it. Okay, so what we do is that, suppose this is our input layer. Okay, maybe any number of neurons. I call it, say, input. Okay, and then you have another layer which we call hidden one, and then another layer which we call hidden two. Okay, so what we do in functional API, right? You give a name to every layer. Okay, for example, this is input, so I have given it a name input. Okay, it is my name. You can call it I, J, K, anything you like. Okay, it's not a keyword, nothing. I'm just calling it input. I have just given it a name, right? And yes, this input is you can say a class. This is specific, right? And here you can give the shapes, maybe 784 neurons or whatever you like. Okay, so we have created this 784 neurons. Now what we do, we create the next layer which we call h1. Okay, what is h1? H1 is a dense layer. Okay, how many neurons? Maybe 120 neurons. What is the activation function? The activation function. So we have created this layer, right? Now you see both of these layers are independent. They are not yet connected. You have maybe for this statement, we have created this layer. For this statement, we have this, but they are not connected yet. So how do we connect it? Basically, when you are creating this layer H1, right, you put these parentheses, and within these parentheses, you give the name of the previous layer with which you want to connect it. I want to connect H1 with input, right? So when I'm creating H1, which is a dense layer, I put these parentheses and I write the name of the layer with which I want to connect it. Okay, now let's do one more layer so that you get the idea. Let's make H2 and connect H2 with H1, right? So what is H2? H2 is again a dense layer. Okay, how many neurons? Say 32 neurons. What is the activation function? You can write here. Okay, whatever activation function you are using. Now with this statement, this layer is created, but it is not connected with H1. So if I want to connect it with H1, what do? I put parentheses and H1. Now it is connected with H1, right? Similarly, if you have H3, you can keep on doing it dense and whatever you have, and you connect it with H2. Okay, so you keep on doing it. Now you see it is very flexible. I can connect anything with anything. It is not just stacking. Okay, you can even merge different layers, which we'll see later, concatenate different layers. So there are many, you can say, options available once you are using functional API. And finally, what you do once you have the complete model, you just say autoencoder is model. You give the first layer and the last layer. Okay, you give the name of the first layer and the last layer. So this is like, you can say, connecting the whole thing together. Okay, so now with this preamble, let's go back to our slides and see if it makes sense to us, right? So you see we say input is 784, hidden layer is 128, and this is our compressed representation, which is 32. Of course you can add more layers. Okay, this is a very simple case study. So we call it input, which is the first layer. Then we have hidden one, which has 128. Okay, and you see this, we are connecting hidden layer with the input layer. And then we have the coded layer, which is again a fully connected layer. We are connecting it with hidden one. Then we have hidden two layer, which is connected with the coded layer. And finally, we have output, which is connected with hidden two. And eventually you have the model, which is, you can say, input and output together. Okay. And as we discussed earlier, the most important part is this one, that when you call model.fit, since there is no y, okay, you just have x. So whatever is input, the same thing is output. So that's why you say model.fit x, and then means whatever is the input, the same is the output. Okay. Now, once your model is trained, okay, it is fully trained. Now, if you want to visually see how good it is, okay, so just like you have the predict function in any architecture, right? You have some test data. Test data means the data which was not used in training the autoencoder, okay, because we just want to see how good it is. If you feed it with training data, maybe the reconstruction is very good visually as well as quantitatively. So we maybe feed it with some unknown data using the predict method. So when you call the predict method is actually forward pass. Okay. So with the forward pass, you are feeding this image and you are getting this as an output, right? Which is pretty good. Similarly, this one and so on. So you see, if the model is trained sufficiently, then you get something which is, you can say, useful. And as we said, you can use it for compression. But the application that we'll see is denoising. I have not introduced it yet. I was just sharing an implementation so that you have some more insight on how it works, right? So if there are any comments so far, we can discuss before we see some, you can say, more details and denoising autoencoder, right? Okay, now we'll be extending our idea of autoencoder from fully connected layers to, you can say, convolutional layers, right? The previous example you had seen, we just had fully connected layer, right? Which is basically the dense layer. Okay, but now what we can do is that rather than this dense layer, I can have basically this layer called 2D. Okay, so we can replace the fully connected layers by convolutional layers. And why do we want to do that? If you remember our very initial discussion, which was the motivation of CNN, when you are using fully connected layer, there is no weight sharing, right? So your parameters grow exponentially. As you keep on adding layers, the parameters just explode, right? On the other hand, in case of convolution, your weights are actually filters, and there's a concept of weight sharing, which means if there's a filter, the same filter is applied on the complete image, right? You don't need a different filter for different parts of the image, right? So that's why the number of parameters in the convolutional layers is much less, you can say, as compared to what you get in a fully connected layer, right? So what we can do is we can actually, just like we were doing with the, you can say, fully connected layer, when we replace them with convolutional layer, instead of just, you can say, some neurons, you will now have volumes, right? Because you have depth now. So you feed it with a colored image and then you apply convolution. Maybe we see a more concrete example with some numbers. So we have 400 by 400 colored image, right? You do convolution pooling, maybe you get 200 by 200 by 3 and so on, right? So eventually this is your compact or compressed representation or the bottleneck representation. It depends what you want, right? You can control the spatial dimensions as well as the depth, right? How much you want, you have all the control. You can use pooling to control spatial dimensions, and you can use the number of filters to control the depth, right? So this part is actually your encoder, and then you have the decoder part, which is actually you can say doing the reverse process, and eventually you are getting this 400 by 400 by 3 as an output, right? So this basically is exactly the same concept. The only thing is that the fully connected layers are replaced by the convolutional layer, right? So now we see how we can use this autoencoder for denoising, right? Now, what is noise? You see, and we are talking especially in the context of images, right? That we have some data which is noisy. Now, why is it noisy? There can be many reasons, right? Uh, Suppose there is some fault in the hardware through which you are acquiring the image, right? Maybe if it's an X-ray machine, it is too old. If it's a digital camera, maybe it fell down. So there's some hardware problem. Okay, this is one possible reason of noise. Now, what are the other reasons? Suppose you have an image, maybe a document, a printed document, which was stored for centuries, right? And then you digitize it by scanning. So over time, the image has degraded, or you have a very old photograph of your grandparent, right? So you just scan them so that you want to preserve them. But since it was physically stored over a long period of time, so physically it is damaged, right? So when you digitize it, so it is noisy, it is corrupted, right? So these are some reasons which can lead to noise in your data or images specifically, right? And we see how we can smartly exploit autoencoder without much sophisticated solution to, you can say, denoise the image. When I say denoise, it means we want to remove noise from the image. We want to have, you can say, a clear or robust picture, right? Okay. Now, how do we do that? This is the key slide which explains everything, right? So first we need to train an autoencoder so that it learns to remove noise from images. Okay. So we do some smartness at the time of training. This is an original image, okay, from MNIST or whatever data you have. We add some noise to this data, right? And we have this noisy image, right? We are intentionally adding some noise. Okay, there are different ways of adding noise, Gaussian noise or salt and pepper noise. Okay, if you are not familiar with them, it's okay. You just have some function to call with some parameters which will add some noise to your data, right? So we had our data, we intentionally added noise to our data, and then we have this encoder part, the compressed representation decoder part, which is basically your you can say convolutional layers if you are talking about a convolutional autoencoder, or if you are talking about a simple autoencoder, these can be fully connected layer, right? So this is actually your autoencoder part. Okay. So in the input, when we are training it, we are giving it a noisy image as input, but as a target, what we are giving it as a target, we are giving it the clean image. Okay. Now you see what we are doing. We are asking the autoencoder that if I give you this as an input, I expect this as an output. Okay. So of course, this is one image. I will have thousands of image of digit 4 as well as of many other digits from 0 to 9. Now, when actually every time you give it a noisy image and you say, I want this 4 or I want 2, right? So your autoencoder will actually learn that, okay, what is the useful information in this image? Maybe this part is the useful information, right? And whatever is here, these intensity values, this is actually the noisy part. So I need to adjust my weights in such a way that I get rid of these and I only keep this specific part of the image, right? So intuitively, this is the whole idea. And now you see, the only thing you will change when training the model is that previously, when we were training the model, we were saying model.fit and we were feeding it with, you can say, whatever is the image and the same thing as an output, right? This was previously that we were doing. Now what we are doing, we want the original clean image as target, but what is the input? Input is actually noisy image. Okay, so in input we have a noisy image, but in output we are expecting, or we are giving as target a clean image. It will force the autoencoder to actually learn robust representation, that what actually is the useful information in this image which I should keep and which I should discard. Now, once the model is trained, right? And again, if it is trained on digits, you should feed it with digits, right? It is not possible that you train it on MNIST and then you start feeding it with some photographs of landscape, so it will not work, right? So now, once it is trained, now you see this is the test data, which is very, very noisy, which we are feeding to the autoencoder. And this is what we are getting as an output. So you see, the noise has been almost perfectly removed. So this is, but of course, again, the limitation is that it can only remove noise from the data, which is similar to the data on which it was trained, right? This is a very big limitation. You cannot always have the same types of images on which you add noise and then train it and then denoise it, right? But still, if you have sufficient data of one type available, it is a very effective technique, data specific denoising technique that you can exploit, right? Okay, do we have any queries so far before we move forward? Okay, now we have seen autoencoders quite in detail, right? And we have agreed that they are used in unsupervised learning, right? Because all the previous discussion we have done, uh, we never needed the class label, right? Because we were not doing classification, right? But just out of curiosity, maybe we can discuss that is it possible to use autoencoder for classification, right? Classification, which is actually supervised learning, right? And we have been saying that autoencoders are like unsupervised learning, but can we somehow exploit autoencoder for classification tasks, right? So let's discuss it basically that whether we can do it, and if we can do it, how can we do it, right? Okay, so again, let's take an example that we make an autoencoder, right? I'll just draw the block version so that we gain some time. Okay, so this is our autoencoder. Okay, you have some data. You train this autoencoder on your data. For each class, we have plenty of examples. Okay, and now this is trained. We assume that this particular autoencoder is now trained. Okay, now what we can do? I can pass all of my data through this trained model. Okay, and for each image, maybe I can extract this encoded representation, right? So I just do a forward pass. I train it, and you can say you can throw away this part. You don't need it any. Once it is trained, since we are not doing a decompression, we don't need this part. We are only keeping this first part. Okay, and now I feed it with my input data, which was say 28 cross 28, right? 784 values, and I am mapping those values to 32 values. Now, MNIST has 60,000 images, right? If I remember correctly in the training set. So each of these images is now represented by 32 values. Okay, so you can make a matrix where you have image number one, you have 32 values here, image number two, 32 values here. So you have a matrix of 60,000 cross 32, right? Previously it was 60,000 cross 784. Okay, now you see these 32 values, you can consider them like feature vectors, that you had raw images which you have converted to a feature vector of size 32, and now you can use this to train any classifier, like for example SVM or any other, you can say classical traditional machine learning classifier, to do the classification, right? Now, instead of feeding this SVM with images, raw images, you are actually feeding it with more useful information, which is a latent representation or an encoded feature vector, right? So in summary, what we did, this is one possibility, right? I'll tell you another one, but in summary, how can we exploit an autoencoder for classification? We can train an autoencoder just like we train it conventionally. Then we can throw away the decoder part. Okay, means we only keep the initial layers, the encoder part and the compressed representation. Then you pass all your data, including training and test, through the trained autoencoder. So all of your data raw data is mapped to feature vectors. In this example, the dimension is 32. So now you have data converted to features, and you can use any, you can say, machine learning classifier to train it and then test it, right? So this is, you can say, you are using autoencoder to represent data into some meaningful features, right? So this is one way you can actually use autoencoder for the classification task. Of course, your actual classifier is this SVM, right? But still, you are actually taking or seeking some help from autoencoder in generating the features. Okay, so this was one option. Another option, which might not be very practical for data in which you have a large number of classes, but it is still very interesting, right? Now, what we do is that, again, suppose we have this problem to solve, which is digit classification. Okay, so here we have 10 classes. Okay, since 10 is a small number, so maybe it is, we can discuss this particular solution for this problem. On the other hand, if you have 1000 classes, then maybe this is not an attractive choice. Okay. Now what we do is we make 10 different autoencoders. I call them autoencoders 0, and then autoencoder 1, and so on up to autoencoder 9. Okay, so you have 10 different autoencoders. Why? Because I had 10 classes. The first autoencoder, which I'm calling autoencoder 0, you train it only with the images of 0. Okay, means all the images of 0 you had, they are used to train this first autoencoder. Similarly, the second autoencoder is trained with images of 1, and similarly your last autoencoder, maybe this one, it is trained only with images of 9, right? So 10 classes, data of each class is used to train a separate autoencoder, and no other class is used in training that particular autoencoder. Okay, so seems a bit strange, but let's see. Okay, now models are trained. Okay, everything is trained. You are done. Now let's see how we can use it for classification, how it will predict. Okay, so the models are trained. I'm assuming model is trained, so I'm getting rid of this training data. Okay, now we are at the test time. Okay. And what happens at the test time? You have a query, maybe this image, and you have to tell the class label that this is 9. Okay, and you already know that this is that one coded for 0, this is for 1, and this one is for 9. Okay, so what you will do is you will feed this query to all the 10 autoencoders which are already trained. Okay, so it means you are conducting a forward pass by feeding your query image to all the autoencoders which you have trained, and their number is same as the number of classes. Now what will happen is, now you should be able to guess. The first autoencoder was trained to produce 0. Okay, when you feed it with a 9, so maybe it will try to predict some, reproduce an image, but it will not be a perfect 9, right? It would be, maybe it is close to 9, but not what we expect. Similarly, this autoencoder will also try to, you can say, generate an image of 9, but maybe not a very perfect version of 9. On the other hand, when you feed this image to the last autoencoder, then we expect it, because it was trained on images of 9 only. So if it sees something which is similar to 9, so we expect it to be, you can say, very close to the input, right? Now, this was for the discussion purposes. How do you implement it, okay, or how do you quantify it? Because when I say it is good or perfect, these are subjective terminologies. Now you see, we already have discussed that you have a mechanism of computing the error between this and this. Okay, you just take mean square error, that how close my approximate is. So what you can do is you pass your query to all the trained autoencoders. You have 10 different output image. Now you compute the error of the original input image with all of these. So if everything is fine, then we expect that this will give you the least error. Okay, because we expect this to generate an image which is very similar to the input image. Why? Because this autoencoder was trained on images of 9. So now you know, okay, this is the autoencoder which produced the least error. And what is the label of this autoencoder? 9, because it was trained on images of 9. You know, you have this information from training time. Okay, so you say the label of this image is 9. Okay, so you see, it's an interesting idea, but of course not very practical if the number of classes is very large. But it is more of, you can say, if you want to just play with things to enhance your understanding, then it's a good idea. But of course, maybe for practical problems, since we are likely to have a large number of classes, so it would not be very efficient if for 1,000 classes I trained 1,000 different autoencoders, right? But still, you can explore it, right? So just a summary of the two approaches that we discussed. The first one was that you have a trained autoencoder, right? You discard the decoding part, right? And then you feed your data to the trained autoencoder, and you take the output from the compressed, or the, you can say, hidden representation, right? So this actually is equivalent to mapping your data to features, right? So whatever encoded vector you have, you consider it as a feature vector. So you can actually use any classifier, maybe ANN or SVM or anything, to actually perform the classification. Second option was that you design autoencoders equal to the number of classes, and then you train one autoencoder using examples of that class only, right? When you have a query image, you feed it to the trained autoencoder and you compute the error between the original and the reconstructed image, right? So if the autoencoder which was trained on the same class as that of the query, it will give you the lowest error, and this will allow you to actually identify the class of you can say the query image, right? So this was just, you can say, a short discussion that how you can use autoencoder for classification, right? So the last thing for this topic is again a variant of autoencoder, right? Which can be useful in some situations, right? Which is called stacked autoencoder, right? How is it different from other autoencoders? The difference is that, in as you can guess from the name, that you be stacking things together, but the difference is that you will not be training it in an end-to-end fashion, right? You will be training some part, keeping it aside, another part keeping it aside, and so on, and then you'll be stacking those together to come up with an autoencoder, right? So let's see some details that how it works. So again, for the example, we'll say, okay, we'll have a stacked autoencoder with 2 layers for mnist digits, right? Okay, so how do we do that? You designed an autoencoder, right? Maybe just like we have been doing previously. So this is your input, maybe 784. You have some layers in between, and this is your output, which is again 784. This is the original value. This is the predicted value with the hat, right? So you train this autoencoder, okay, with with the complete 60,000 images you have in your MNIST dataset. Now, once this autoencoder is trained, okay, what you do again, you throw away this decoder part, okay. You pass all the 60,000 images through this trained autoencoder, and they will give you this representation, right? Which we are calling H1, or we are calling primary features. Okay, so it is the same thing which we did previously, right? But there is something afterwards. Train the autoencoder, throw away the decoder, pass your data, convert all your data or map all your data to primary features, which we are calling H1. Okay. Now in the second step, what we do is we don't need the images anymore. Okay, we say, okay, this is my data. And what is this? These are the primary features H1, which you learned from the first autoencoder. Okay, so now you say, okay, just forget, we don't care from where these are coming, maybe images or anywhere. Now this is my input data. Okay, now there is no need of images. So I design another autoencoder where this is my input and this is my output. Okay, so from this I am trying to predict this, and so on for the you can say other neurons. You can train this complete autoencoder, and then you have this representation. Again, you throw away this part. Okay, you pass your complete data through this, and you have the features which we are calling H2 or secondary features. right? Because they have been learned from the primary feature. The input to this autoencoder was primary feature, and you trained it, and now you have secondary feature. So you can repeat this process as many times as you like. But since we are considering 2 layers only, so now what you have here, okay, for every image you have this representation. Okay, you can then use these as features, and you can train any classifier, maybe ANN or SVM, just a software classifier, and you can do the classification. Okay, so if you see the global picture, you see it is something like that. But the difference is that we are not training it in an end-to-end fashion. Using this, we train an autoencoder to learn this. Okay, means at one point in time, we are training this part. Once this is done, then we take this green part as an input and we train an autoencoder to learn these secondary features. And of course, you can keep on doing it many times and eventually you say, okay, now I have a good representation. So this is my final feature vector. I will use it with the classifier and I can do the classification, right? So you see, this can be very useful if you want to do something, but you don't have much of computational resources, right? Because at one point in time, you are not loading everything in the memory. You just have one level of features to train. And then once that part is trained, you throw away everything and then you start from the scratch using the trained features, right? So you see it is basically stepwise training. So this could be very useful if you have limited memory, limited computational resources where end-to-end learning is not possible, right? This was stack autoencoder. There are of course many variants of autoencoder, but we'll not be discussing them. But anyways, I'll just be telling you their names so that if anyone is doing research in this area, they get familiar with that. These are also options, different options available, right? So a very common variant is sequence to sequence autoencoder. How is it different from what we have seen? Basically, when we have designed autoencoder, either we are using fully connected layer or a CN, like convolutional layer. In sequence to sequence autoencoder, we have something which is called RNN. We have not seen it yet. We'll see it maybe next week, inshallah, right? But still, just like you can implement an autoencoder with fully connected layers or a CNN, you can do that with a recurrent neural network, which we will see from next week onwards. Then you have variational autoencoders, which are like generative model. Again, generative models we'll see when we see GANs, right? And there's another variant which is called sparse autoencoder, where instead of having very few neurons in the hidden representation, we have a very large number of neurons, right? And most of them are actually not active. When you say sparse, it means scattered, right? There are very few neurons which are active and most of them are inactive, right? So these are few of the variants which are not part of our course content, but I have just mentioned their names so that if in the literature you ever come across these, you can correlate with the discussion that we have had, right? So with that, we conclude autoencoder, and if you have some questions, we can discuss those.